So here are the current assignments and when they're due. We've got section 1.7, the written assignment due tonight, right, and the web assignment for that's tomorrow. So just 1.7 is due tonight, okay, and then tomorrow 1.8 along with the web assign for 1.8. Okay. So last time we covered the lecture on section 2.1. Let's take a look at a couple of the assignment problems in there. So we've got 17 to 25 odd. Oh, nothing too. So let's look at 24. So section 2.1, number 24. We have the function defined, h of t is equal to t plus 1 over t. Right, remember we talked about defining functions algebraically using algebraic expressions, and this is a function defined as such. And it simply asks us to evaluate h of negative 1. So for h of negative 1, right, this is h of t. Replace t with negative 1. And what do you get? Minus 1 plus 1 over minus 1. 1 over minus 1 is just minus 1 again, so you get minus 2. H of 2 is equal to, well, for every instance of t, you put a 2. So this is 2 plus a half, right, which is 5 halves. H of 1/2, h of 1/2, right, for every instance of t, you put a 1/2. So this is 1/2 plus 1 over 1/2. Right? 1 over 1/2 is equal to what? What's 1 divided by 1/2 like that?
2.
It's 2 again. So it's a half plus 2 is 5 halves. Notice it's the same as that. And the reason being, just in general, they ask you to evaluate h of 1 over x. Right? So for h of 1 over x, what do I do? Right? H of t is equal to t plus 1 over t. And this is saying for every instance of t, put 1 over x. So the first instance of t becomes 1 over x. The second instance of t becomes 1 over x. And then 1 over x, similar to this one up here, becomes what? One over x just becomes x. Right? Whenever you have 1 over a fraction, right? Well, it's the numerator fraction times the reciprocal of the denominator. But the numerator is just 1, so it just becomes the reciprocal. just in general. Okay. So 1 over x just becomes x over 1, which is x. And this happens to be the same as h of x. Right? If we were to replace the t with x, we get the exact same thing. And then lastly, it asks you to evaluate h of not 1 minus x, but x minus 1. And so that becomes x minus 1 plus 1 over x minus 1. Right? So you could just leave it at that. So that's 24. Plenty of similar problems like, 20. We were supposed to be doing the odd numbered ones. Why did I do the even? Let's make sure that's not one I assigned. I don't think it was. Okay. 34, 38, and 70. Let's look at 34, which is one that was asked that I asked you to hand in. So let's do one similar to it. So number 33. Which is one of the odd ones. So we'll do 31 and 33. So number 31. So this type of function in 31 through 35 is called a piecewise defined function. Essentially, the domain of the function is broken into pieces, and on each piece, the function is defined differently. So this one says f of x is equal to, and then they use a big brace like this to denote it, x squared if x is less than 0, and x plus 1 if x is bigger than or equal to 0. So the domain of this function is all real numbers. Okay, and right, because you can plug in whatever value for x that you want, either x less than 0 or x bigger than or equal to 0, and then the value of the function is a polynomial, and that's always defined. So the domain for this function is all real numbers. But they take the domain and they cut it into two pieces: negative values of x and non-negative values of x. All right, so they ask in 31, what is f of negative 2? So for f of negative 2, the value that we're plugging in for x is negative. Right, so because x is negative 2, we're using this piece of the piecewise function, and therefore f of x is equal to x squared. So this becomes negative 2 squared, which is 4. F of minus 1, well, what's that going to be equal to? Which piece of the piecewise function do we use again? To
negative 1 squared.
Negative 1. This top part or the bottom part?
The top.
Top piece, right. So because negative 1 is less than 0, the value of the function is given by x squared, which in this case is negative 1 squared, which is 1. All right, f of 0. Which piece of the piecewise function do you use when x is equal to 0? The top piece or the bottom piece?
Is it the bottom?
It is the bottom, right? When x is bigger than or equal to 0. So the 0 belongs to this piece. All right, not this one. This is for x is strictly less than 0. So this is 0 plus 1, which is 1. f of 1, use the bottom piece. Is 1 plus 1 is 2. And then they ask for f of 2 as well. Again, use the bottom piece because the 2 is bigger than or equal to 0. So it works like that. So for different values of x, we use different pieces of the piecewise function. Which piece? Well, it tells you right there. (33) another piecewise determined function, this time with 3 pieces. So x squared plus 2x, if x is less than or equal to minus 1, x less than or equal to 1, and minus 1 if x is bigger than or equal to 1. And then they give you a string of values of the function to evaluate. F of -5, which piece of the piecewise function do we use for x equal to -5? Top, middle, or bottom?
Top.
Top one. Right, so that's -5 squared plus 2 times -5. 25 minus 10 is 15. F of, actually it was supposed to be f of -4, that one, sorry. F of -4, still the top one. Minus 4 squared plus 2 times -4. So that's 16 minus 8 is 8. And then f of -3/2. Which piece of the piecewise function do we use here? -3/2 being -1.5. So which piece do we use? Top, middle, or bottom?
Top one.
Top one again. So -3/2 squared plus 2 times -3/2. So that's 9 over 4 minus 3. So 9 over 4 minus 12 over 4, so that's -3 over 4. F of -1. Which piece now for x equal to -1?
The top.
Top again. X less than or equal to -1. So that's 1 minus 2 is -1. F of 0. What about f of 0? Top, middle, or bottom?
Middle.
Middle, right? And then f of 0 is just 0. F of x is just x in that case. And then f of 25. 25 uses the bottom piece. And that function, the value of the function f, is always -1 for x is bigger than or equal to 1. Okay, so those are piecewise defined functions. We'll do a little bit more with them, in the next couple sections. So you have number 34 to do, which is just similar to those two. 38 and 70. What's 38? Same kind of things that we've been doing. Let's do 30, 35. 35 is a good one. So in 35, we have f of x equal x squared plus 1. So now let's evaluate f of x plus 2. F of x plus 2. So what do I do? Well, f of x is equal to x squared plus 1. So f of x plus 2, wherever you see x here, you replace it with whatever the expression here is, x plus 2. So this is x plus 2 squared plus 1. And if we were to put this in standard form, this is x squared plus 4x plus 5. Now, it also asks you to evaluate f of x plus f of 2. Well, what is f of x?
X squared plus 1.
That's just x squared plus 1. Now, plus, right, this is f of x right here. What about f of 2? F of 2 squared plus 1. So this becomes x squared plus 1 plus this number here is 5. So that's x squared plus 6. By the way, are they the same? F of x plus 2 and f of x plus f of 2? Are they the same? Are they?
No.
No tricks here. Are they?
No.
No, not the same. So notice, right, f of x plus 2 is not the same as fx plus f2. So in number 38, you'll be comparing f of x over 3. In 38, you're going to be evaluating, not over 3, f of x over 3 and f of x over 3, and they're going to be different as well. Okay, most functions don't respect division. Don't distribute over division or multiplication. Some do. Some functions distribute over multiplication, division. No functions except for just multiplication on its own. Other than just multiplication on its own, no functions distribute over addition. Did I say addition before? Multiplication or division. But addition, nothing. And then I asked you to hand in number 70. So find the domain of these various functions here. So number 66, it's a good example. So I asked you to do number 70. Let's do number 66. Is that one of the assigned ones? 51 to 65 odd. Well, let's do 65 first. We'll do 65 and 66. So 65, find the domain. For f of x equal to, square root 2 plus x over 3 minus x. Okay, well, again, the domain of a function in this context, in this algebra, calculus, track context, the domain of a function is the largest set of values upon which the function is defined. Right? So the largest set of x's that allow this function to be defined. Well, with multiplication and with addition and subtraction, there's never really any problem. It's only when we take roots, even roots, square roots, fourth roots, sixth roots, not with cube roots and fifth roots, but with even roots, trying to take the even root of a negative number. So for this to be defined, okay, we need that 2 plus x is bigger than or equal to 0, and 3 minus x is not 0. Right? Anything but 0, because you can't divide by 0, you don't want to take the square root of a negative number. So this says that x is bigger than or equal to negative 2, and this one says x is not equal to 3. Right? So here's the domain. So here's negative 2, and here's the 3. We want to leave out the 3. And all the numbers x bigger than negative 2, except for 3, work. Right? So the domain is the interval from negative 2 to 3, not including 3, union the interval from 3 to plus infinity. Number 66, similar to that. So find the domain of this function. F of x, or not f of x, it's g of x this time. G of x equal to square root x over 2x squared minus x plus x minus 1. All right, so for this to be defined, we need, well, the x has to be bigger than or equal to 0 in order for the square root to be okay. And we also need that 2x squared plus x minus 1 is not 0. Right? Solving an equation equal to 0 and an equation not equal to 0, it's the same thing, really. I mean, you solve where it is 0, and then you say your solutions are everything but that. So here, this one factors 2x plus 1, x minus 1, I think. Yeah, equals, or not equals 0. So that means 2x plus 1 is not equal to 0. And this time it's and rather than or. So 2x plus 1 is not 0, and x minus 1 is not 0. And this says x is not equal to negative 1/2, and this one says x is not equal to 1. Right, so our domain is all the x's bigger than or equal to 0, but not x equal to 1. So, here's 0, here's 1. All right, and we put an open circle at the 1 because we're not including it in the domain. And And then since we're only interested in x is bigger than or equal to 0, the negative 1/2 has no effect on the answer. So the domain for G is the interval from 0 to 1 union the interval from 1 to plus infinity. Okay, so 64, or no, what did I ask? I forget. 70, right? 70 is similar to that. Yeah. 70 is somewhat similar to those. All right. Okay. You guys, if you just give me just a moment, I will be right back. Okay. Alrighty. Moving on to section 2.2. Is on graphs of functions. So, first thing to notice is the following: given a curve in the xy coordinate plane, okay, we say it satisfies the vertical line test when every vertical line intersects the curve in at most one point. Either intersects it once or not at all. Okay, so something like this. So this curve, and I'm going to put these solid dots here, and right above that I'll put this open dot. So this curve, and this is the x-axis, this is the y-axis again, this passes the vertical line test. Right, so this vertical line intersects once. This vertical line over here intersects not at all. And this vertical line here also intersects once. Now, you may say intersects twice, but the meaning of that open dot so this intersects once, intersects once. Now, you may look at that and say, well, that intersects twice. The meaning of that open dot, the closed dot, is where the curve is, right? This notation of the closed dot that we've been using for a while is that, you know, with intervals on the real line, on just one horizontal line, is that the closed dot, you include that point. The open dot, it acts as like a boundary. It tells you where the boundary is, but you don't include that boundary point itself. So this vertical line, it intersects the curve, this broken curve, just once. passes through this boundary point, but that's actually not part of the curve. It's just a boundary point. And then it intersects at the closed dot right there. Okay, so that vertical line intersects only once. This one not at all. This one once. And the other one is going to be once as well. Okay, so this curve passes the vertical line test.
You keep cutting in and out.
Oh, I'm sorry. The sound is bad.
And the video also.
Is the video? If I do this, it's going to disconnect entirely. Well, let me do it anyway. Are you guys still hearing me?
I can hear you now.
Yeah, is that any better, or is it still cutting out?
You haven't cut out yet.
Okay, all right. So far, so good.
Do you think you could go over this example again?
Yeah. So
Thanks.
this example here, this curve, this broken curve, it passes the vertical line test. This vertical line doesn't intersect it. So vertical line test is not that it intersects once, every vertical line. It intersects at most once. At most once means once or not at all. This vertical line intersects once. This vertical line intersects once. You may look at it and say, oh, I think it's twice. Okay, but the open dot, what the meaning of that is it's a boundary for the curve. It says the curve is working its way up to that point, but doesn't actually get to that point. Right? The closed dot means that point is included in the curve. So this point is included in the curve. This point is not. It simply acts as a boundary for this right-hand piece. Okay? So when we look at this now, we see it and say, oh yeah, it passed the vertical line test. This one doesn't. So the, good old circle, that does not pass the vertical line test. So this vertical line intersects twice. Right, so this curve fails the vertical line test. Again, x is the horizontal axis is x, and the vertical axis is y. So when you have a curve that passes the vertical line test, it defines a function. Is my voice cutting out at all?
Nope.
Good. It defines a function as shown. So here's an x-axis, here's a y-axis, or instead of the wrong way. The horizontal is the x, the vertical is the y. Here's a curve. Okay, looking like that. And we'll label the curve y equals f of x. And what this means is if you take an x value of, whatever, if you go up or down to the, we'll say this is 1, x equal to 1. If you go up, actually let me not use that point. It's going to be sloppy looking. Let's use this point. So we'll say x equal to 2 right there. If you go up or down to the curve, right, then once you hit the curve, you go horizontally to the y-axis, and you're going to get a certain value. You say 1.5 maybe. Right here, so that's negative 1.5. And right here, for example, This will be negative 2. All right, so what this curve is telling us is that f of 2 is equal to the corresponding y value that the curve defines for you. Right? Here's the x value. We go vertically to the curve. Once we hit the curve, we go horizontally to the y-axis. So the x-axis represents the domain values. The y-axis represents the range values. And that's why we say y is equal to f of x. Right? So let's write that down. Right? Domain values are on the x-axis, and corresponding y values are the values for the range f of x. So y is the value of the function, x is the domain value. So here, the value of function f at 2 is 1.5. The value of function f at 0, say, is that, which is, I don't know, 1.75. F of 0 is 1.75. Right? We take x equal to 0, we go vertically to the function, and we hit the function here, and then you go horizontally to the y-axis, and you get some value on the y-axis. Here it's 1.75. And we don't have to move horizontally at all, because we're on the y-axis to start. F of negative 1.5. So here's domain value x equal to negative 1.5. The corresponding y value is what? So if x is negative 1.5, we hit the graph of the function right there. We don't have to move vertically up or down. Therefore, the corresponding y value is what?
Well, 0.
0, right. 0 on the y-axis. And right here, f of negative 2, let me put this closer to here. F of negative 2 is negative 1.5. We go to 2 here, we go vertically to the function, and then horizontally to the y-axis. So at x equal to negative 2, domain value negative 2, we get range value negative 1.5. Okay, so, and you need that the curve passes the vertical line test to do that, because for the way a function is defined, every domain value gives you one range value. When you don't pass the vertical line test, you can't do that. I mean, if this is x is equal to 1, well, which y value do I use? This one or this one? Domain value x equal to 1, range value y equal to this or y equal to that. Well, I mean, it doesn't make sense. There's no reason to pick one over the other. Okay, and if there was a reason to pick one over the other, then you wouldn't have two intersection points. You'd only have one. Really. So let's look at another one of those. Another example. Well, let's go back to this one here. This one that we drew. And let's label some points here. So we'll say this is x equal to minus 1, y equal to positive 1/2. We'll say this is y equal to 3/2 right there. Y equal to 1 right here, corresponding to x value 1. And then let's take a look at these points here. So let me make this a little bit higher. So we'll say that's x equal to 3. And this point on the y-axis we'll say is 2. And this point on the y-axis is 2.5. And then right here, x equal to 3.5 right there. Okay, so on this curve, okay, f of minus 1, you go vertically to the function, and then you go horizontally to the y-axis, and you get a range value. Oh, sorry, you have to call the curve y equals f of x. So we're looking at the function defined by this curve. So f of minus 1 is equal to positive 1/2. What is f of 0? Right, if we take x equal to 0 and then we go vertically to the function, then we've hit y value what? Well, what's labeled there?
3/2.
3/2. And then this open dot, close dot thing. Remember, the closed dot means that's where the curve is. The open dot is just sort of a placeholder. So f of 3 is equal to what?
Two.
Is equal to 2. Is not equal to 2.5. F of, say, 3.01. So if you move slightly to the right of 3, then we hop up here. So that's going to be equal to like 2.49 or something like that. Right? F of 3 is 2. But f of 3.01, once we move slightly to the right, we hop up to there. You know, so that value is close to 2.5. And f of 3.5, again, you go vertically to the function, and then horizontally to the y-axis, and that's equal to 2. Okay, but slightly to the left of the 3, f of, so f of 3 was 2, f of like 2.99, that's going to be equal to what? Well, again, it's this part here. So it's close to 2. It's like 1.99 or something. But a little bit less, right? Right, here's 3, and then we hit the function at 2. If you went slightly to the left of 3, then you're right about there, like 1.99. If you go slightly to the right of x equal to 3, then you pop up to here. Okay, so that's what this hop and this break in the graph, that's the effect it gives you on the values of the function. Of course, we like functions that aren't broken, so-called continuous functions. You know, but that's a different story. All right. So given a curve that passes the vertical line test, that gives you a function. Similarly, if you've got a function whose domain and range are the real numbers, that can give you a curve. So conversely, f of x, whose domain and range are real numbers. Okay, the function defines a graph. Y equals f of x, which will be a curve that passes the vertical line test. Okay, so, there are, of course, linear functions. So f of x equal to mx plus b, right? Or, for example, f of x equal to minus 1/3 x plus 1, or forgot the x, right? That defines a line, y equal to f of x, which in this case is mx plus b, right? Which we've talked about extensively already back in chapter 1, right? So here, if we have y equals f of x, now if we know what f of x is, right, we usually just write y equal to that, minus 1/3 x plus 1. If we don't know what the function is, we'll write y equals f of x. Right? But when you know what f of x is, you simply replace f of x with the expression for the function. So here, this linear function gives you a line. So the y-intercept here is 1. The x-intercept here is 3. And that's the easiest way to to graph a line, just to find the x and the y-intercepts. That should be black. Now, by the way, there's often this kind of notion that one should put these arrows to signify the fact that the line goes towards, towards infinity in each direction. There's no real reason to do that. I mean, it's ugly. That make your pictures nice. So, if it didn't come out quite as nice the first time, do it again. There we go. So that's the x-axis, that's the y-axis, and this is y equals minus 1/3 x plus 1. So that's a linear function. And then there's some kind of standard functions that one should be aware of. So the basic parabola. So f of x equal to x squared. So if you want to look at the graph defined by this function, it looks like this. And it's nice and symmetric from left to right. Bilateral symmetry for all your biology folks. So I'm not drawing it with bilateral symmetry, but much better. So this is the graph y equals x squared. Now all quadratic functions will basically be riffs on this that we'll see later. So this, again, this is the x-axis, this is the y-axis. So, like, here's the origin, right? F of 0 is 0. And then, you know, f of 1 is 1, but it's also the same as f of negative 1. F of 1 is equal to f of negative 1 is equal to 1 squared. F of 2 is equal to f of negative 2 is equal to 4. So in that case, well, I have not drawn it to really show that, but it's going to be way up here. Oh, it's going to be ugly looking. I'm not going to do that. Let's move the picture down. Let's try it again. All right. So f of 0 is 0. F of 1 is equal to f of negative 1 is 1. And I'm not going to draw it to scale here. All right, so the 1s on the x and the y-axis are in different places, so it's kind of smushed down. F of 2 and f of negative 2 are both going to be at 4. On the y-axis. So on the x-axis, values of 2 correspond to values of 2 squared, which is 4. On the y-axis, for 3, x values of 3 correspond to y values of 3 squared, which is 9. So at 3 and at negative 3, we get negative 3 squared, or 3 squared, which is 9. So that's a standard function, f of x equal to x squared, and its graph, y equals x squared. It's one to remember, right, to put that one in your memory. Later, we'll find that all quadratic functions f of x equal to ax squared plus bx plus c are variations of the basic parabola f of x equal to x squared. Later we'll do those. Another one. Again, a standard function. Right? Well, we were talking about the fact that x squared plus y squared equals 1. Well, what curve does this define? x squared plus y squared equal to 1. It's not written y equals f of x, so the curve that it defines doesn't have to pass the vertical line test, and it doesn't. Right? This one defines the circle of radius 1 centered at the origin, 0, 0. Right? This is not the graph of a function. It's a curve, so for every x value you get corresponding y values. Well, for every x value you'll get, 1 or maybe 2 corresponding y values. But that's not what you want. To get a function, basically you just take parts of the curve that will pass the vertical line test. Right? Solving for y in two different ways. This is the graph of a function. Fx equal to square root 1 minus x squared. And it's the top half of the circle. If you want the bottom half, well, that's just the negative square root 1 minus x squared. So this is y equals square root 1 minus x squared, right? I mean, you can square both sides of this, and you get y squared equals 1 minus x squared, and bring the x squared over here, right, and get back to this equation. But here, with this equation, you get the full circle, because that's just the distance formula for any point xy from the origin of distance 1. Well, any point of distance 1 from the origin is along the circle of radius 1. Okay, but here we're insisting that y is positive. Y is the positive square root 1. What happened there? Y is the positive square root 1 minus x squared. The bottom half is the graph of the function fx equals minus square root 1 minus x squared. Okay? So some things that we know how to graph already, just, sort of recast into function form. Piecewise functions is the last thing I want to cover. That's a little bit, takes a little bit of thought at first. So graphing a piecewise function. Just be careful of which piece it is you're graphing. So we'll say f of x is equal to, and I'll define a piecewise function here, 1 half x plus 1 if x is less than negative 4. 2x plus 3 if minus 4 is less than or equal to x is less than 1. And we'll say minus x if x is bigger than or equal to 1. Notice each piece of this piecewise function is linear. So I'm going to have 3 lines. Okay, I just have to be careful where I place each line. So Let's get an x and a y axis. Actually, that's too close. So where are my three pieces of the domain? Well, I want x is less than -4. So we'll say -4 is right there on the x-axis. And then also at 1. So we change pieces at -4 and at 1. So here's 1. All right. For x is less than -4. So this piece is x is less than -4. So for x is less than -4, I use this, the -1/2 x plus 1. Well, at x equal to -4, if I were to plug x equal to -4 into this, although I'm not supposed to evaluate the function, but to get the boundary point, I need to do that. I would get, so -4, -2 plus 1 is -1. So here's -1. And right there, I'm going to have an open dot. And then to the left of that, it's a line of slope 1/2. But at x equal to -4 itself, I'm supposed to use this, 2x plus 3. So that's -8 plus 3 is -5. So that's actually down here, and that gets the solid dot. And then at x equal to 1, this is 5. So that's going to be up there. And then we cross the x-axis at 3. Use the line tool. We cross the y-axis at 3. And then x equal to -1 for x is bigger than 1. So for x is bigger, I'm supposed to have an open dot there. -x, so -1 is here, so that's the solid dot, and then slope -1 goes down 45 degrees. Okay, so there's three pieces, 3 lines, so the domain was broken up into these 3 bits. X is less than -4, x is bigger than 1, and the ones in between. And each one uses 3 different lines, but we only graph pieces of that line, so what's left over passes the vertical line test. We'll do some more examples of these tomorrow. We're out of time for today. Okay, so that's all for section 2.2. Don't forget about the assignment due tonight, and tomorrow we'll go over some problems for 2.2.